This will go faster than it did in the one-dimensional case. We're going to talk about position and displacement vectors in 2 dimensions and higher order dimensions, and what happens with distance. And honestly, it's about the same as what we found with 1 dimension. When we're dealing with 2 dimensions, we'd have our xy coordinate system. By tradition, 0, 0, the origin would be where we measure our position vectors. So I'm going to keep position vectors in the white. Actually, hold on. Let's color code this a bit better. We'll only have the coordinate system in white. So yellow, the color you see right underneath position, those are going to be for position vectors. So let's say we have a position vector r1, and it moves to a position vector, and the object moves to a position r2 over some amount of time. So start here, end there. All right. Those are position vectors. If you try and write down a position vector, it would look like x1 in the I hat direction for the first one, y1 in the j hat direction for the first one, and similarly for the second. In higher order dimensions, we'd just add a plus z k hat, and so on if we had higher than 3 dimensions. All right. What becomes of displacement? So displacement will be in green, the color I'm underlining here. Displacement will tell you how you go from one place to another. It is delta r. Delta r will be your final r minus your initial r. And if we look at this carefully, if we plug these in, it would be, x2 minus x1 in the I hat, and y2 minus y1 in the j hat. Now, this isn't really worth memorizing, except that the displacement delta r is r final minus r initial. But there you go. So displacement's pretty simple. It's just the difference between 2 positions. Okay, and position continues to be the location relative to the origin. All right, I said we'd cover this pretty fast, and we are, because we are up to distance. The simplest way of thinking about distance is that it is the absolute value of the displacement, or the magnitude of the displacement. If you want to find the magnitude of the displacement, that can basically be found by taking the dot product of the displacement with itself and taking the square root. Actually, by the time we do that, we don't need to take the absolute value anymore. So I'll just write it as dot product and square root. Okay. In other words, it actually ends up being the square root of x2 minus x1 squared minus y2 minus y1, whole thing squared. If no direction change. So this works great for finding the distance traveled between any 2 points that are adjacent in the time stream. So if you have r1, r2, r3 in order from t1 to t2 to t3, then to find the distance traveled between r1 and r2, you'd do exactly this. To find the distance between r2 and r3, you'd basically do x3 minus x2 squared minus y3 minus y2 squared, and take the square root. If you want to find the total distance for those motions, the 2 motions, 1 to 2 and 2 to 3, you'll have to add the distances. So distance remains the magnitude of the displacement. Okay. So that is it for part 1. We're going to come back very quickly, talk about what happens with velocity vectors. and speed. And then we'll move on and talk quickly about acceleration vectors, and then we'll actually get into the meat of the chapter.